Just give me a quick thumbs up if you can hear me and also see my screen.
We see and hear loud and clear.
Okay, perfect. Yeah, thank you so much. Thanks everyone who's joined today and taking the time out for attending this one. I'm very excited to present my work on evaluating and enhancing the performance of large language models in clinical settings. So this problem is both timely and impactful as these models are rapidly making a move into healthcare. And let's start quickly with the structure of the talk. So I'll begin with background on clinical LLMs, their capabilities, and the rate of adoption. Then we'll identify some key failures and challenges, and I'll walk through the three different research projects, each addressing one of the challenges we identified. And finally, I'll discuss how my work impacts the community. All right, so we've seen LLM score impressively on medical examinations. GPT and Gemini, among other models, get over 90% on these examination style questions, which are pretty standard, and there's an MCQ sort of options to choose from. But these setups are very clean and controlled, and there's no real clinical messy notes involved. However, real clinical use looks very different. And the high test accuracy does not guarantee that these models are safe or reliable when they want to write medical notes or even interact with patients. So, that benchmark to reality gap is the starting point for my work. So, why does this matter now? And that's because LLMs aren't future tech, they're already in care settings, they're also in our everyday life. Also, we've seen that Epic and Microsoft have integrated GPT-4. This was back in 2023 for documentation support and so on. And like we just discussed, that people are increasingly using AI chatbots for medical information directly. And this market is only expanding rapidly, projected to go over 430 million in the next couple of years. So we have a widespread deployment, but the evaluation methods haven't caught up. So this creates a real world risk and not just an academic concern. So supporting this argument, recent work has shown that our standard benchmarks often don't reflect real clinical performance. And another work, which reviewed about 500 research articles on LLM evaluations, mentions that only 5% use real patient data, which is kind of concerning. So, as these models look strong on paper, they don't really translate to being safe or reliable for patient use. So, let's just sort of bring this question back where what does reliability actually mean in clinical practice? So, if we look at how clinicians work, it's not just about knowing the facts, it's also about how they are updating their information, verifying, and communicating it with patients over time. Let's start with the first one, which is knowledge augmentation. So, as we know, medical knowledge, along with any knowledge, is not static. There are new drug approvals, there's new research going on, and guidelines sort of change all the time. So, clinicians stay current by checking resources like up to date or recent literature. However, LLMs, which only rely on the data that we're trained on. So, as medicine is moving forward, these models can sort of fall behind. The other challenge is sort of comes with verifying facts, where clinicians just don't trust their memory. They also verify, they look at patient records, guidelines, and cross reference facts. So LLMs also generate this really long, fluent text, but they sort of mix correct and incorrect claims, and they also sound very confident doing so. So subtle hallucinations can slip through unnoticed with these current evaluation methods. All right, so another everyday reality is that different patients phrase questions differently, and that could be based on their education, background, or demographics. So a clinician is supposed to give the same answer, but when we tested, LLMs sort of struggle with this. So these everyday behaviors give us three reliability issues for LLMs in healthcare. One is keeping up to date with the knowledge, verifying facts, and instruction sensitivity. So let's go over my contributions, which addresses each of these challenges that we have surfaced. So my first contribution targets the stagnant medical knowledge. I built Beacon, which is a framework to let LLMs pull more updated, like more relevant and updated information on the fly instead of relying on a frozen training snapshot. In short, in this way, we're helping models stay current as medicine also evolves. The second contribution focuses on factual verification. As we have seen, LLMs generate long texts, which are hard to evaluate, and especially for factuality. To address this, I built another framework that breaks the long text into atomic claims, and we check each of them against the source. This lets us evaluate factuality at a very fine-grained level. The third contribution looks at how LLMs respond to changes in how instructions are phrased. So we analyze how stable or unstable the LLM responses are given these changes. All right, so together, this work sort of develops both methods to evaluate and improve the reliability of LLMs. Let's start with the first one, which is tackling the problem of stagnant knowledge. So as we've quickly seen that LLM has a static snapshot, unlike medicine, which is evolving. And the current idea here, a core idea here, is to see that LLMs need a way to update their knowledge at inference time. To study this problem rigorously, we needed a task where the impact of missing or outdated knowledge can be measured very precisely. Named entity recognition offers exactly that. It isolates the model's ability to correctly recognize the specialized medical terms and allowing us to quantify how much augmentation helps. And I'll get to the details a little bit. I might be using a bunch of new terms, but we'll look at them in a minute or so. So this involves extracting structured information. Like in this example, given the sentence, we're interested in extracting diseases, which is cystic fibrosis. And we evaluate performance using a metric called entity level F1 score, which we'll get to in a bit. All right, so to sort of work off from the side for this idea, we had to select some data sets. We chose data sets called ChemProt, CDR, and CBI. These are just names, but the most important thing is the entity types that we're looking in each of these. So they are all the way ranging from proteins, chemicals, to different, let's say, pico elements and medications. So they together span a wide range of biomedical contexts. And we evaluate this approach on both closed models like GPT-4 and Claude V2. So this was my work back in 2023, and these were the state-of-the-art models at that time. And we also use an open model, which is Llama 270B. And the goal was to test if this augmentation strategy provides benefits across the full spectrum. So I know I've used a bunch of terms, so here's a quick review of what each of them mean. So this is an input sentence from which we want to extract the entities from. And these sentences are from the abstracts in the data set. Entity types are the categories into which we want to extract these items into. So here the categories are proteins, chemicals, diseases, and so on. And finally, entities are the exact items from the input sentence we want to extract. In this example, it's amino acid, BRCA1, BRCA2, etc. Okay, so let's just continue using the same example where we have the sentence and we're extracting diseases. And so we prompt the LLM with this information, and the LLM incorrectly labels BRCA1 as a disease, although it is a gene. In our method, we retrieve the formal definition of this gene from a repository like UMLS. To simplify, we can also use something like Wikipedia, and then ask the model to take another look and refine its output. So the model then processes this information and updates the final answer, which is indeed correct. So let's call this strategy singleton, where we append all the information about all the entities at once. But in more complex scenarios, where you have multiple entities extracted, it gets kind of complicated because the model has to understand the definitions of all of these terms and also correct the JSON at the same time, the output, when I mean JSON. So to keep it simple for models, we explore another strategy where we simplify the task by asking one question at a time. So here we start with one entity and ask if this entity belongs to this entity type given its definition. And we sort of repeat this up until all our entities are done, and we programmatically edit the JSON. Here, the task of LLM is very much simplified in the sense that it just needs to return a true or a false. And we call this iterative prompting. So let's look at some results. For GPT-4, with this method, the improvement was across the board. We've seen about a 15% relative gain. And this shows that even strong closed models benefit from this method of targeted on-the-fly context. For models like Claude, although singleton did not improve the scores as much because, as we just discussed, it's slightly complex. With iterative strategy, there was up to a 30% gain across all the data sets. So it sort of also proves that when you break down a complex task, for the models that need more explicit guidance, this method works pretty well. All right, so we built a framework to provide relevant and updated information to the LLM. And we also proved that this method improves the performance on downstream tasks across the board. All right, this directly ties back to our work of updating LLMs with otherwise static snapshot knowledge that they have. Just take a quick second here. So the second major reliability challenge we address is the fine-grained factual verification. So in the previous NER setting, the evaluation is pretty clean because we have a structured output. We have a ground truth, which is also called the golden answer, which we have gotten from experts. So it was very easy to match something like a disease, which is cystic fibrosis, to the correct answer and get our scores. But in this case, where models generate long free-form clinical text, as they do in practice, evaluation becomes far more difficult because there is no ground truth to refer to, and both correct and incorrect statements are sort of woven together in a single narrative. This only gets worse when we're working with clinical notes, and which are kind of underexplored in research, but also very essential and a safety critical domain to work on. So I developed a method which breaks down the clinical text into atomic facts. As you can see in this sentence, the first sentence is broken down into 3 different atomic facts. And an atomic fact is the smallest indivisible unit of information. So now we can go ahead and independently verify if each of this fact is true or false using something called entailment. So what is entailment? Let's start with something super simple. Let's say there is a statement which says John owns a golden retriever, which is a fact. So that's the premise. And another statement says, which is a hypothesis, says John owns a dog. So in this case, it is entailed. The hypothesis is entailed by the premise, because if John owns a dog, and if golden retriever is a type of dog, John owns a golden retriever is also sort of true. So let's say that this is entailed. But if someone said that John owns a cat, then that is not entailed. All right, so let's just take this phenomena and apply it to our original clinical note. So we have the original note as the premise and the first fact here as the hypothesis. And because this hypothesis is correctly reflected in the premise, the entailment is 1. And in this example, as it is an incorrect statement that the model generated, the entailment is 0. So this allows us to calculate our metrics like precision and recall, which we'll get to in just a bit. So again, we had to choose some data sets to sort of make a proof that this works. And we've worked off of 2000 clinical notes from a bunch of different sources like Mimic, Medaline, and Coral from 3 different hospital systems. And we also use 4 different clinical types of clinical documents, because this helps us cover a range of dense technical writing found in the real clinical notes. All right. So this was again back in 2024. So the then state-of-the-art models were GPT-4, O1 Mini, Gemini 1.5, and so on. So we use those state-of-the-art models. And we also use GPT-4o as our LLM as a judge after rigorous evaluation and validating it with human judges. So we measure, again, quick review on LLM as a judge. So because we have a lot of data points, it's very hard to use human evaluations to scale up. So we use a subset of human evaluations. We use our LLM as a judge to scale that up, and we calculate something called a Fleece-Kappa score. So Fleece-Kappa score is just a measure between multiple annotators, which is how much do they agree beyond chance. And values above 0.6 are generally considered substantial agreement. And for our LLM as a judge, we have that about 0.67, and this makes our judge reliable enough to be an automatic evaluator. Okay, so here's an end-to-end pipeline we developed. First, we use an LLM to decompose each note into atomic facts. And then we evaluate these facts in an entailment framework that we just discussed, where the hypothesis is the node and premise is each of these facts and so on. And we also validate our judge against subset of humans, and we do a quick qualitative study as well. So the collection of these 3 million or so hypothesis pairs and 3,000 expert annotated pairs is the data set that we've released called Factor. Okay, so I said we'd discuss a little bit more about metrics, so let's do that here. As we've seen earlier, LLM breaks down the clinical note D into something called facts, which are C of D. So to calculate precision, we want to see if how many of the generated facts are actually supported by the original clinical note. So in this case, the premise is the full note, and hypothesis is each of the fact that the model extracts. And we then have LLM as a judge to score this as entailed or not entailed. A high score here means that model hallucinates less and it generates more factual information. Another metric is recall. So for that, we split our original note D into S of D with a sentence parser. In this case, the premise is the set of all the facts that the model generates, and hypothesis is each sentence in the clinical note. So this is how much of the original information the model keeps when generating facts. So using these scores, precision and recall, we calculate F1. So moving on to results, we want to see how good LLMs are at generating correct facts. When we compare these F1, we observe that GPT-4o is on par or slightly better than O1 and consistently outperforms smaller models like Llama. And even on progress notes, the discharge summary and discharge summaries, we observe the same pattern where O1 and GPT-4 are really good at generating more facts, but also more accurate facts. And so to provide further analysis, we do an in-depth qualitative evaluation with experts. And we focus on 3 dimensions than simple entailment that we just discussed. So atomicity is a measure to see if the fact is a minimal unit of information. So as I said, we want to sort of decompose each of a sentence into the minimal actionable sort of facts. So let's just use this example throughout for the rest of the qualitative evaluation and see that on the left we have the note, and on the right we have the facts that the model decomposed our note into. And we see that the model incorrectly says, it sort of like combines a bunch of information into the second one, where it says pleural effusion is left-sided and increased from last scan, which is not atomic, as it talks about multiple criterion. Followed by independence. This is to test whether a fact stands on its own. So following the same example, the second fact says it is left-sided. So when you independently look at this fact, you cannot really make sense of what it could mean. So this is not independently understood. And finally, correctness, which is slightly similar to like entailment. We see that if this fact is exactly what it reflects in the original note. When we compare these results, we see that even qualitatively, obviously matching the quantitative numbers, GPT-4 shows high degree of correctness and independence, as annotated by a medical expert, and a perfect atomicity. But on the other hand, we see that Llama struggles with both atomicity and correctness. And this is obviously because Llama is a much smaller model, also an open model, so it comes with its own drawbacks. So this methodology overall shows that to evaluate LLMs reliably, we must verify correctness at individual fact level and not an overall score. All right, so let's now look into the third reliability challenge that we've identified. Okay, so in this work, we inspect how robust are small open language models to natural variations in how instructions are faced. So up until now, we were sort of working off of the more popular GPT and Gemini and so on. But in this study, we specifically focus on smaller language models, which are faster and cheaper to deploy. And you can do that in-house, which sort of works around the whole HIPAA and the other constraints with data privacy. So to analyze this comprehensively, we selected a diverse set of real-world tasks, including classification and several extraction tasks. For classification, we have a prompt, which in this work we call an instruction, and the relevant clinical note, and we expect the model to output a yes or a no. And we measure this performance with a metric called AUROC. And for extraction, we do something similar where there's an instruction, the relevant clinical note, and we expect the model to generate a list of the entities, as opposed to yes or a no in the previous section. Okay, so the data sets that we've chose here were modality prediction from Mimic 3, 9 classification tasks, and 6 extraction tasks from Mimic derived. Mimic is basically a very large repository of medical notes from about 10 years of a hospital here in Boston. Yeah, and we extract these data sets from something called N2C2, and these sort of provide the complex, messy real-world clinical notes. And we chose 7 different small language models, and we compare their general domain based models like Llama and Alpaca against clinically tuned counterparts. So when I mean clinically tuned, it's that you take a general domain model like Llama, continue to train it with a bunch of medical information, guidelines, clinical notes, etc. And that sort of resulted in a couple of models like Asclepius. You do this on Alpaca, and that's MedAlpaca, and so on. These were released by different research groups across the world. So now that we have the data sets, models, and the metrics set up, the important next step in this work was to gather the exact instructions that I was talking about. So we worked with 12 medical professionals from 10 different countries to write down these instructions for each of the 16 tasks that we just looked at. So this ensured that we captured the real world diversity. So let's focus on one task here, and here's an example of the instruction. Based on the notes, please indicate blah, blah, blah. So the thing that we're interested in is for this task, the instruction from one medical expert slightly differs from another medical expert, but eventually we're still asking the model to look at this note, determine XYZ, and indicate a yes or a no, which is basically how person A to person B would prompt an LLM right now. Yeah. So when we used all of these instructions and prompted the models, we found something interesting. So we observed very high variance in performance, which was particularly evident in models like MedAlpaca, which were clinically tuned. And the general domain models were slightly more robust and actually better performing than the clinical domain models. This could be surprising, but this sort of corroborates previous work in this domain. We also do a quick fairness analysis to see if there is a disparity between the performance on male and female patients, and these are sort of slight different variations, but there's still some impact. And we also sort of see that on white and non-white patients to some extent. So this means that instruction sensitivity can also give you a very large distribution in performance, but also worsen existing disparities. So this sort of concludes the idea that small language models are not robust to these changes in instructions. All right, so to quickly summarize, we've identified and addressed 3 different challenges in this presentation. We saw that knowledge augmentation helps us bring in relevant medical information. The fact verification frameworks helps us judge claims at a more granular level. And instruction sensitivity uncovers a potential flaw in these models. So let's now take a step back and see the overall impact of where I see this work going and its general impact on the community. So some of this work is getting a lot of traction outside academia, especially FACTOR, the framework to evaluate models more granularly. I was also featured at HAI, and other works have been referenced referenced in biomedical research. The bigger impact, though, is the shift in mindset that we're evaluating LLMs in a way that they're actually used with real patient language, evolving knowledge, and the safety in communication. So I hope this helps support safer use of AI in healthcare. And I'm very grateful to all my collaborators across multiple institutions who made this work possible. Thank you for your time, and I'm happy to take any questions.